Hello and welcome to this quick review looking at pH curves and indicators. We'll cover the use of continuous monitoring techniques to record the pH during the course of titration. And doing this allows us to look at what happens before, during and after neutralisation. So when we're talking about an aqueous solution during the course of titration, it's important to remember what's going on in terms of the ratio of hydrogen ions to hydroxide ions. Now obviously all aqueous solutions due to the dissociation of water will contain some H plus and some OH minus. But overall, if the ratio is in favour of H plus, so there's more H plus than OH minus, the solution is considered to be acidic. If it's the other way around, the solution is considered to be alkaline. And if at any point the solution has equal amounts of each, it's considered to be neutral. So in all three of the situations described, you will be getting H plus and OH minus reacting to make water. But it's the overall net concentration of either H plus versus OH minus that we're interested in, as in which one is in excess. And this change in the relative ratios of them is what a pH curve hopes to show in graphical form. So let's have a look at what a pH curve actually looks like. So this particular example shows a strong acid, strong base titration. So at the beginning, the solution is acidic because you can see that the pH is very low at the start. As more base is added, an increasing amount of aqueous H plus ions are converted to water by reaction with OH minus. Now the OH minus is obviously coming from the base that's added. So where you get a vertical section of the curve, this is called the equivalence point, and at this point exactly the right amount of OH minus has been added to neutralise all of the hydrogen ions originally present in the aqueous solution of the acid. Now between 26 and 50 centimeters cubed of added base, the OH minus is now in excess, so the solution becomes increasingly alkaline until eventually it will reach the same pH as the added base and the curve will start to level off again. So let's summarise this on the diagram. So as you go from left to right, adding more and more base, obviously the pH increases and H plus in aqueous solution, its concentration is decreasing. So prior to the equivalence point is acidic, but the curve steepens as the equivalence point is approached. It's neutral at the equivalence point, and for a very short period of time, the vertical section represents the point here, and the actual neutralisation happens in the middle of the vertical section. After the vertical section, the solution is alkaline until the pH of the base is reached and the curve will level off. So there's actually different types of pH curve shapes depending on the type of acid-base titration that's being undertaken. So I've given you 4 different scenarios here and a little bit of information describing what each curve will look like. Why don't you pause the clip and see if you can sketch all 4 of these axes and put the correct curve shape in. And whilst you're doing it, try to use the descriptions I've given to help you. Obviously you'll have your independent study materials and notes. See if you can do it without copying from them this time. So you should end up with something roughly looking like these 4. The key thing is to make sure that the neutralisation point, the middle of the vertical section, is at the appropriate part of the pH range. So for strong acid, strong base, it's pretty much in the middle. Strong acid, weak base is a bit further down because the strong acid is determining when neutralisation takes place. With weak acid, strong base, it's the strong base that dominates its position, so it's a bit higher up, and it's a bit hard to tell for weak acid, weak base. Okay, the next thing to look at is how would we use a pH curve in quantitative terms. How could we mathematically use it? And this depends on not just the volume of the base added, but the concentration of that base, so you know how many moles of base you're adding at any given point. So you can use first year chemistry here, N equals V times C, to calculate the number of moles of base added at any given time. So in this particular example, the number of moles of OH minus aqueous at the point of equivalence is 2.5 times 10 to the minus 3 moles. And we can use the balanced equation for neutralisation, which I've popped up towards the top of the screen, to deduce that this required an equal number of moles of H plus in aqueous solution. So that would mean we can also make some deductions about the number of moles of acid required. So here's another exercise for you. Pause the clip and see if you can calculate the theoretical number of moles of each of these acids that's required to achieve this equivalence. And while you're at it, have a think about why the actual shape of the curve might not look like the one in the picture. So a little bit of thinking here. Pause the clip and give it a go. So making the assumption that the addition of the base is forcing all the dissociations in these two acids to run to completion, that would mean that you'd require 1.25 times 10 to the minus 3 moles of H2SO4 and 8.33 recurring times 10 to the minus 4 moles of H3PO4. Because what I'm doing in each case is looking at the number of moles of OH minus that I need and dividing it by the number of hydrogens that I have available, 2 in the case of H2SO4, 3 in the case of H3PO4. So you may recall a couple of minutes ago I asked you to suggest possibly why the shape might not match the one in the graphic. It's because the graphic shows the pH curve for a monobasic acid. In other words, one neutralisation. But looking at H2SO4, which is dibasic, and H3PO4, which is tribasic, you'll get 2 and 3 separate neutralizations. So as you move through the neutralizations by adding more and more base, the curve shape actually changes because each neutralization will be more and more a weak acid species being neutralized. But before we get too ahead of ourselves, I just wanted to bring your attention to the fact that this would be extension only. This is not going to be on an examination, it's just an extension of the idea of a pH curve. Because some pH curves for different acids that you might come across if you were to go and look them up online, for example, might have slightly weird looking shapes like these, and I just wanted to give you a quick explanation as to what's going on. Okay then, let's move on to indicators very quickly before we wrap things up. So an indicator is a weak acid which has a different colour in aqueous solution to its conjugate base. So different indicators will reach their endpoint, which I'll explain in a second, at different pH values or ranges, and this is because as they're different weak acids from each other, they'll have different Ka values to each other. So let's take the equation to represent damp litmus paper. So this is what's going on the actual paper itself, with a bit of water added to it. So this makes the litmus indicator go into aqueous solution. So the undissociated weak acid is red in aqueous solution, but the conjugate base of that weak acid, once it dissociates, is blue. What you've got to do is think about it like an equilibrium. So if H plus is added, i.e. it's dipped into acid, the position of the equilibrium shifts to the left to use up the excess H plus. The solution turns red, so the piece of paper turns red. So if you add excess OH minus, or dip the paper into an alkali, the position of the equilibrium this time shifts to the right to introduce H plus aqueous into solution to use up the excess OH minus. At the same time, you'll produce blue conjugate base in aqueous solution. As the concentration of this increases, the solution turns blue. So the end point of an indicator is the pH range at which the weak acid concentration is equal to the conjugate base concentration. In other words, when the colour changes. It usually occurs within 2 pH values. So what you need to do is choose your indicator so its endpoint matches the equivalence point or vertical section of your titration as closely as you can. So looking at the values on the diagram on the left hand side, you can see from the different titrations which ones would work. For the first one, all three would be fine. The second one, methyl orange, would be ideal. The third one, phenolphthalein, would be the best choice. So this brings us to the end of the short review we were going to do on pH curves and indicators. Hopefully it's put some of the things into perspective for you, given you a little bit of clarity. As always, it's a good idea to now go and try a few exam type questions on this area. But in the meantime, thanks for listening and see you soon.